Hello everyone. We are starting a free open lecture in our Discord. All our lectures are held weekly without breaks. If you, the viewer, want to ask questions online and get answers like join our lectures, you can find the link to Discord in our Telegram channel. To find out the schedule of the lectures, join our Telegram channel. If there are more than our processing cores in total, then competitive execution will occur for each of these cores, and thus, for example, just as an example, we have the first request that takes 1 second, the second and third on other cores also take 1 second simultaneously, but the fourth, fifth, and sixth, which also arrived at this time, will first wait until a core becomes available. Each of them, specifically, in this scenario, respectively, and only after waiting, after just 1 second, when the first 3 requests are completed, they will start executing. And accordingly, the time here will also grow linearly, but not as quickly, because we can process several requests in parallel, not just one. Well, accordingly, this topic can be done on different scales in various ways. The simplest thing is that we do this on several cores of one processor, which allows us to efficiently manage tasks and processes in a streamlined manner, and then we can create small clusters, connecting other computers where we can execute all of this, thereby enhancing our computational capabilities and performance, and this can scale to any size depending on the requirements and load on our application, ensuring flexibility and adaptability in various scenarios. So, let's consider how to do this in plutonium parallel computing, a method that optimizes resource utilization and maximizes throughput. We need the multiprocessing module. The feature of multiprocessing is that it essentially allows us to launch another process, and in this process the function we pass will be executed. Essentially, in order to successfully and effectively execute this, at the same time these processes will be independent and operate independently, simultaneously. Actually, no, not like that. In fact, they will have different resources, for instance. They cannot, for example, but this can certainly be implemented. That's why we will use the multiprocessing module here so that 2 processes can exchange data. We have our process, but the application itself and the process we launched, that is, this function. And in order to have the function return a desired, anticipated, and expected outcome or result, we utilize this particular structure. So we create QI specifically to
Want to become a great programmer? Subscribe to our Telegram channel.
processes could simply exchange data, and we create a process function here. We pass the brand, which need to be passed to this process that we start, and here we just wait for it. And after it has completed, we calculated our sum in a loop and place the result in the queue. Accordingly, the queue is essentially shared between these 2 processes. So if it is essentially shared, we can basically put into it in one process and read from it in another. Essentially, this allows for efficient communication between processes. Well, actually, as anticipated, we got the outcome, and then after deliberate consideration we returned it, usually in real programming languages like C++. This is done through threads, because threads can be executed in parallel. Threads are modules like threads, trading, and so on. But Python is not a real programming language, and threads are synchronized using JLA, so here trading works a bit differently than in other programming languages. Here, we use multiprocessing for true parallelism. Well, let us take a moment to see how exactly the requests and inquiries will be processed during this particular instance. Each request, as we can see, is processed in approximately 1.3, 1.5 seconds on average, which is already much better. This is certainly not 1 second. There are also various overheads, nearly half a second. But this definitely arises because we create a process here, start the process, and then we also need to terminate the process. There is a kind of IO-bound load that appears because we definitely need to wait a little. Right now at this moment, this is the waiting time, but it gradually accumulates here. But, as we can see, on a 6-core processor. Each request is already executed truly in parallel, because the time is the same everywhere, and this time is around what it would take to execute just one request. If we, for example, send more requests than I have cores on the processor, let's say approximately 20 requests or so, it is evident that the average execution time of one request has become about 3 to 4 seconds. While there are challenges, using parallel computing is still much more efficient than trying to do the same tasks without it, as it saves time and enhances performance. Then, of course, the first request would take 1 second, the second 2, the third 3, and so on, 4. The 20th would take 20 seconds. But here, everything is done in 3 to 4 TFSP. This is significantly better, almost 6 times faster. And another application of parallel computing which is particularly effective and efficient in video processing, or when a neural network is computing something such as image recognition tasks, is that we can execute requests in parallel. This means that here I have one request on one core, then there's a second request on the second core. Finally, there's a third on yet another separate third core. You can also split just one single request across multiple cores. And it will indeed turn out that the time of the request itself will be significantly reduced several times. Let's say the request initially took 1 second. We parallelized it across 3 cores for one request, and it now executes in 0.33 seconds. And then we reduce the request time accordingly so that they will queue up but be processed a bit faster. This means that in this case we had 3 individual requests per second, and now we will have 3 individual requests per second. We can also combine all these types of optimization as we wish, especially if we have many cores and additional computers available for computation, which is often the case in modern computing environments. For example, we can apply this first method of parallel computing on different computers, meaning our application is connected to some computer, and we send one request to each computer, allowing them to execute in parallel, thus improving efficiency. Furthermore, on each computer, the request processing will also occur across multiple cores, maximizing the use of available resources. Accordingly, we will be able to significantly reduce the processing time of a single request overall as well, and also create this queue to the system, expand it a bit to accommodate more requests. It will take not one request, but several. This will allow the queue to handle multiple requests simultaneously. They will be executed in parallel immediately, right away, and this can also be refined further, likely, reducing the complexity of the algorithm, and it will work super fast. Are there any questions? Sharp real language we program? I don't know, thanks. See you next time. There we will talk about how all this parallel competitive synchronicity calculations look like and what happens in the process.
Want to become a great programmer? Subscribe to our Telegram channel.